Let us see what happens when atoms with different electronegativities combine to form a covalent bond. When two atoms with different electronegativities combine to form a covalent bond, the electron density between atoms is shared in such a way that it is displaced more towards the more electronegative atom. As a result, the more electronegative atom gets a partial negative charge, while the less electronegative atom gets a partial positive charge. The partial positive and negative charges on the dipole are indicated by the symbols delta plus and delta minus respectively. Therefore, in heteroatomic molecules in which the two atoms differ considerably in electronegativity, two electric poles develop. We say that the molecule has developed polarity. The covalent molecule with the two oppositely charged poles is called a dipole. For example, the dipole in hydrogen chloride is represented as shown here. Hence, the bond is called a polar covalent bond, and the molecule is called a polar covalent molecule. Examples of polar covalent molecules are hydrogen fluoride, hydrogen chloride, water, and nitrogen trifluoride. When atoms with the same electronegativity combine together to form a covalent bond, such a bond is said to be a non-polar covalent bond. Here, no polarity is developed in the molecule as the shared electron pair lies exactly between the bonded atoms. Molecules with non-polar covalent bonds are called non-polar covalent molecules. Examples of non-polar covalent molecules are hydrogen, fluorine, chlorine, oxygen, and nitrogen. Let us now move on to the concept of dipole moment. The polarity in a polar covalent molecule is expressed in terms of dipole moment. Dipole moment is defined as the product of the magnitude of the charge and the distance between the centers of the positive and the negative charge. Dipole moment is denoted by mu and is equal to the product of charge q in coulombs and distance of separation r in meters. Dipole moment is a vector quantity, which means it has both magnitude and direction. The unit for dipole moment is called dBi and is denoted by d. 1d is equal to 3.33564 into 10 to the power minus 30 coulomb-meter. Dipole moment indicates the degree of polarity in a molecule. Dipole moment is represented by a crossed arrow starting at the positive pole and pointing towards the negative pole. For example, the dipole moment of hydrogen chloride is represented as shown. The crossed arrow indicated above a Lewis structure indicates the direction of electron shift. In case of polyatomic molecules, the dipole moment depends on the individual dipole moments, called bond dipoles, and on the spatial arrangement of various bonds in the molecule. The net dipole moment is the vector sum of the dipole moments of all the bonds present in the molecule. Let us calculate the dipole moment of some molecules. Consider the beryllium chloride molecule. It is a linear molecule with a bond angle of 180 degrees. In the beryllium chloride molecule, two beryllium chlorine bonds are present in opposite directions. As chlorine is more electronegative, the shared electron pair moves closer to chlorine, so that it acquires a partial negative charge while beryllium acquires a partial positive charge. The bond dipole between the two beryllium and chlorine bonds is represented as shown. As the two equal bond dipoles are in opposite directions, their vector sum is 0. So, the net dipole moment is 0. Let us take another example. A water molecule. In a water molecule, there are two oxygen-hydrogen bonds. It is angular in shape with a bond angle of 104.5 degrees. Oxygen being more electronegative, the shared electron pair between oxygen and hydrogen stands very close to the oxygen atom. So, the oxygen atom gets a partial negative charge, while hydrogen gets a partial positive charge. The bond dipole lies towards the oxygen atom. The net dipole moment is the resultant of the two bond dipoles of oxygen and hydrogen bonds. The net dipole moment, mu, in water is 1.85 dBi. Now let us take the example of a boron trichloride molecule. In this molecule, 3 boron-chlorine bonds are present at an angle of 120 degrees to one another. The resultant dipole moment of any two boron-chlorine bonds is equal and opposite to the third boron-chlorine bond dipole, as shown here. Hence, the net dipole moment is equal to 0. Let us take the carbon tetrachloride molecule. As the resultant bond dipoles, as shown here, are equal and in opposite directions, they get cancelled, and the net dipole moment of the molecule is equal to 0. It is really interesting to know that different molecules with the same geometry or shape may have different dipole moments. Let us consider ammonia and nitrogen trifluoride molecules. Both of them have pyramidal shapes with a lone pair of electrons on each nitrogen atom. But the dipole moment of ammonia is greater than that of nitrogen trifluoride, though fluorine is more electronegative than nitrogen. There is an explanation. The dipole moment of ammonia is 4.9 into 10 to the power of minus 30 coulomb-meter, while that of nitrogen trifluoride is 0.8 into 10 to the power of minus 30. In the ammonia molecule, there is a lone pair of electrons on the nitrogen atom and 3 nitrogen-hydrogen bonds present in the molecule. The bond dipole is directed towards nitrogen, as it is more electronegative than hydrogen. The resultant dipole moment is in the same direction of the orbital dipole due to the lone pair of electrons on the nitrogen atom. The nitrogen trifluoride molecule has a lone pair of electrons on the nitrogen atom and 3 nitrogen-fluorine bonds. Since fluorine is more electronegative than nitrogen, the bond dipole is towards the fluorine. The resultant dipole moment is in the opposite direction of the orbital dipole due to the lone pair of electrons on the nitrogen atom. Hence, the dipole moment of ammonia is more than that of nitrogen trifluoride. Hence, we can conclude from the polarity of bonds and dipole moment that a covalent bond has a partially ionic character. Based on the Fajans rule, we can say that ionic bonds also have some partial covalent character. To know about the partial covalent character in an ionic bond, we should know Fajans' rules. According to Fajans' rule, when two oppositely charged ions approach each other, the cation attracts the outermost electrons of the anion. Due to this, the electron cloud of the anion gets distorted. This is called polarization. The tendency of the anion to get polarized by the cation is called polarizability. As a result of polarization and polarizability, the positive and negative charges decrease on the cation and anion. This means that the electronic charge becomes more concentrated between the two bonded atoms and is responsible for the development of a covalent character in ionic compounds. If the extent of polarization is small, then the bond is more ionic in nature. If the extent of polarization is more, then the bond is more covalent in nature. The smaller the size of the cation, the greater is the covalent character of an ionic bond. For example, lithium chloride is more covalent than sodium chloride because the size of the lithium cation is less than that of the sodium cation. The smaller cation has a higher electron density, and hence it can distort the electron cloud of the anion easily. The larger the size of anion, the greater is the covalent character of the ionic bond. For example, sodium iodide is more covalent than sodium chloride because the iodide ion is larger than the chloride ion. For an anion of large size, the electron cloud on it is loosely bound to it, and hence can be easily distorted by the cation. The larger the charge on the cation or anion, the greater is the covalent character of the ionic bond. For example, stannic chloride is more covalent than stannous chloride because the charge on tin in stannic chloride is 4, while it is 2 on stannous chloride. On the other hand, sodium sulfide is more covalent in nature than sodium chloride because the charge on the sulfide ion is greater than the charge on the chloride ion. Cations of the same size and charge, the cation with an inert gas configuration forms compounds with more ionic character. The cation with pseudo-inert gas configuration, that is, with 18 electrons in the outermost shell, forms compounds with more covalent character. For example, copper 1 chloride is more covalent in nature as compared to sodium chloride. Copper ion with pseudo-inert gas configuration has an electronic configuration of 2, 8 and 18. Sodium ion with inert gas configuration has an electronic configuration of 2, 8. Lewis' concept does not explain the shapes of molecules. In 1940, this drawback led Sedgwick and Powell to come up with a theory to determine the shape of a molecule. The shape of the molecule is based on the number, type, or extent of repulsions between electron pairs present in the valence shell around the central atom respectively. This theory is named as valence shell electron pair repulsion theory, or the VSEPR theory. It was further developed and redefined by Gillespie and Nyholm in 1957. The valence electron pairs surrounding the central atom in a molecule mutually repel with each other. Thus, these electron pairs surrounding the central atom arrange themselves in space in such a way to minimize the repulsions, giving the molecule a definite geometry. The molecules in which the central atom is surrounded with only bond pairs, then it is said to possess definite geometry, as in case of BF3. As the electron pair is a negatively charged cloud, the bonded atoms move apart to minimize repulsions between the electron pairs. To minimize the repulsion, the distance between the atoms has to be maximum. To attain the maximum distance between the bonded atoms, imagine the valence shell to be a sphere and the electron pairs located on its surface at maximum distance from each other. The shape of a molecule depends upon the number of valence electron pairs and their arrangement around the central atom. The geometry of a molecule, in which the central atom does not have a lone pair of electrons, will be regular without any distortion. For example, the shape of a molecule with two bonded electron pairs around the central atom will be linear, with a bond angle of 180 degrees. The shape of a molecule with three bonded electron pairs around the central atom will be trigonal planar, with a bond angle of 120 degrees, and so on. In a methane molecule, 4 hydrogen atoms are bonded to one central carbon atom. Since the electron pairs have the same charge, they repel each other and try to stay as far away from each other as possible. As a result, all the 4 hydrogen atoms arrange at 4 corners of a tetrahedron, lying at equal distances away from each other. Hence, methane has tetrahedral shape. In the methane tetrahedron, the bond angle is 109 degrees 28 minutes. However, the geometry of the molecules gets distorted due to the presence of lone pair of electrons. Unlike bonded pairs that are shared between two atoms, the lone pairs of electrons are localized on the central atom. Due to this, they occupy more space, which results in greater repulsion. Thus, the geometry of the molecules with lone pair of electrons differ from the expected or regular geometry of the molecules having only bond pairs. In a molecule, the repulsion between lone pairs of electrons is always maximum. Thus, we can say that the repulsion between two lone pairs of electrons is more than that of a lone pair bond pair, which is greater than that of two bonded pairs. Assume a multiple bond to be a single electron pair. Therefore, the presence of multiple bonds will not affect the shape of a molecule. Now, let's analyze the shapes of some molecules with reference to their valence electron pairs. In ammonia, the central nitrogen atom has 3 bond pairs of electrons and 1 lone pair of electrons. The ideal geometry of the molecule with 4 pairs of electrons would be tetrahedral. However, the lone pair of electrons repulses the NH bonded electron pairs, thus reducing their bond angle to 107 degrees and giving the molecule a pyramidal shape. In a water molecule, the central oxygen atom has 4 bonded pair of electrons and 2 lone pair of electrons. We have seen that repulsion between lone pair, and lone pair bond pair is more than bond pair. Thus, the 2 lone pairs on central oxygen atom makes the molecule to distort from its regular geometry to bend or V-shape, making a bond angle of 104.5 degrees. A sulfur tetrafluoride molecule is seesaw-shaped as its bond angles are at an angle of 101 and 173 degrees. Due to the lone pair of electrons present on its central atom. The chlorine trifluoride molecule is T-shaped and its bond angle is 87 degrees and 40 minutes, and the molecule shape is distorted due to the 2 lone pair of electrons on central chlorine atom. In a molecule of bromine pentafluoride, the central atom bromine has 5 bonded pair of electrons and 1 lone pair of electrons. Therefore, the geometry of the molecule is distorted, octahedral or square pyramidal. It is due to the presence of a lone pair of electrons on central bromine atom. In a molecule of xenon tetrafluoride, the central xenon atom is surrounded by 4 bonded pairs of electrons and 2 lone pairs of electrons. The geometry of the molecule is distorted to square planar from the regular octahedral geometry. It is due to the presence of 2 lone pairs of electrons on its central xenon atom.